Hello and welcome back to this recording of TCP and You. My name is Chris Gabrielson, and this is part 2, our TCP deep dive, where we're going to get into the nuts and bolts of how this protocol works and what it's capable of doing. Now, the way we're going to accomplish that is through three major sections. To start, we're going to look at TCP performance in a nutshell. Essentially, what is the maximum speed of any individual TCP socket based on the values that get negotiated in the three-way handshake, which we learned about in the previous section. Once we understand what our TCP performance can look like and what the maximum theoretical throughput is, then we're going to cover a little bit about packet loss. And we're going to try and demystify some of the mechanisms that TCP uses to account for it. Specifically, TCP retransmissions, TCP fast retransmissions, and TCP duplicate ACKs. And then finally, towards the end of this section, we're going to cover some of the less common pain points that might contribute to the TCP protocol acting a bit less throughputy than it should. And that's things like fragmentation, MSS, and bears. Oh my. But before we get into the next section, let's go ahead and quickly review. In three-way handshake in part 1, we talked a little bit about window size. This is dynamically allocated when we first set up the connection, and then as time goes on, the clients, either client or sender, have the ability to adjust the window size in order to make it dynamic as the data transfer completes. So at first, we'll usually start with a very small window size. We'll send a little bit of data, and assuming that data does not get lost, we will increase the window a little bit. We'll send some more data. If it doesn't get lost, we increase a little bit more and more and more until eventually we get to a point where either the clients hit their own maximum or they're in an area where it's comfortable and it's a balance of packet loss, latency, and a few other things. Now, what we care about when it comes to window size is that if the window becomes full, meaning the window size tells the client how much data can be sent before an ACK must be received. So clients are constantly going to be sending data, and they're keeping track of how much data has gone unacknowledged. If the amount of unacknowledged data equals our window size, the client will actually stop transmission and wait until it receives an acknowledgement for some of that data, simply because there's just too much there and we cannot exceed this window size. But what does this look like in terms of a visual? Well, the way I like to accomplish that is with a pretty simple question centered around a very small window size example. Let's imagine you have a window size of 1460 bytes, and this is equivalent to exactly one 1500 byte packet. In addition to this window size, you have a round-trip latency of 1000 milliseconds, or 1 full second. What would the maximum theoretical throughput be for this transmission if there was no loss? And if you kind of do some quick math in your head, you might say, well, if I can only send a single 1460 byte packet, and it takes 1 full second to send it and then receive an acknowledgement before I can send the next block of 1460 bytes, then the throughput should be 1460 bytes per second, or 11.6 kilobits per second. And I get that number by multiplying 460 bytes by 8 in order to convert it into bits. And if you looked at the animation here, you could see a little bit about what this would look like, although this animation is a little bit slower than a full 1 second round trip time. Let me back it up and we'll look through it one more time. Regardless, what you're going to see is the client will send data and then it will stop sending until it receives an acknowledgement. So here, my client is sending data. It gets received by this server. The server sends an ACK, And now that the data has been acknowledged, I can send the next block of data. This is kind of a silly example though, because we're dealing with an extremely small packet or extremely small window size and an extremely high latency, and that's not typical of what you see in a network. Instead, we're going to have something a little bit larger where we can get multiple packets and a latency that's much shorter. So let's scope this up just a little bit. Now, let's pretend we have a window size that is 10 times larger. So instead of 1460 bytes, it's 14,600, essentially 10 packets worth. And our round trip time also gets cut by a factor of 10. Instead of 1000 milliseconds, it's now 100. What would the maximum theoretical throughput look like? Now, depending on if you need to pause the video, go ahead. If not, well, knowing that we had a tenfold reduction in latency and a tenfold increase in the amount of data we can send for that same block of latency, it's essentially going to be 100 times faster. Our answer would then be about 1.16 megabits per second. And I get that number simply by taking my payload data of 14,600 bytes, multiplying it by 8 to get 116,800 bits, and because my round trip time is 100 milliseconds, that means I can get 10 round trips in a full second. So I'll take this window size payload, multiply it by 10, and that's where I get 1.1 megabits. In terms of what that will look like for our clients here, our client, assuming it's operating at something like a 100 meg or 1 gig interface, it'll be able to transmit those 10 packets very quickly, but then it'll be forced to stop and wait for an acknowledgement from the server. Only when it receives that acknowledgement will it then be able to send the next block. Let's take a look at what that looks like. Here we have all of our packets are created and sent in one big burst of 10 packets. Once they're received, they get acknowledged. This one acknowledgement acts all 10, at which point the next block of 10 can start going out, and then it gets acknowledged. And this will continue for however long the transfer needs to based on what sort of data we are moving. But once again, reality is a little bit different. And ACKs typically don't get sent at the maximum size of the window because it's kind of a bad thing if you're sending data and then all of a sudden you're forced to stop because you have this super small window size. Instead, what happens a lot of times is the destination will constantly send ACKs as it's receiving the data in order to constantly keep that available window size free. So in the animation that follows, we're going to change up a couple of things. First off, I'm going to have a column here that actively tracks the current number of bytes in flight. So we're going to start off with 10, and the first packet I send will bring it down to 9, the next one to 8, to 7. That way we can see what the sort of available count looks like as this is going on. Additionally, latency is a real thing in the real world. So whenever we have a client send something, rather than go straight across, we're going to represent latency by having it go at a bit of a diagonal, because once it's left the device, it's going to take some time before it actually gets received, and then when the response comes back, that will also take some time. So when I send a packet up here, I may get the acknowledgement down here. Let's take a look and see what this is going to look like. I start off sending datagram 1, 2, 3, 4. And right when I'm sending 4, I'm seeing I'm just starting to get acknowledgments for some of the first packets that I sent back. And this process is continuing and going back and forth. We could see the remaining window size is constantly fluctuating based on what's going on. And I don't know if you notice this, you'll see I have this datagram number 4 is kind of highlighted out here a little bit, and there's a very specific reason for that. In the real world, whenever we send a datagram, because there is always a non-zero latency, we will typically get the acknowledgement for a previous datagram well after when we sent it. And if we look at what I have snapshotted here, right when we were sending datagram number 4 was when we received the acknowledgement for datagram number 1. I'm going to back the recording up so we can look at that one more time. Pay attention to the path of datagram 1 and then see where we are when we go to do that transmission. So here's our datagram. It's going across, gets to the server. This generates ACK number 1, and right here, right between sending number 4 and 5 is where I received an acknowledgement for datagram number 1. Why do I call out this particular example? The reality in terms of real-world troubleshooting means that this sort of scenario is extremely common, and it's also an example where engineers frequently get confused when they go to look at the sequence and ACK numbers. I have in this diagram below, where my mouse is circling, this is part of an actual packet capture that I was analyzing. I added a column within Wireshark to look at the sequence numbers, and we could see here packet number is here on the left. This is the time since the beginning of the capture, then the sequence number, and obviously the packet data. And these are two packets that are essentially in order of one another. So I'm sending this one with sequence number ending in 17900, and then the next packet from this source now has a starting sequence number of 19332. If I look down below, I could see that there are some acknowledgments. This first ACK is still coming from the same source, but this bottom one here for we got 4 fours, well, that's a mouthful, 4444 19332. The mistake that a lot of engineers make is thinking that this acknowledgement for sequence ending in 332 is for this packet here, number 328049. That is not correct. This acknowledgement is for packet number 328048. And I've got some of the math here in the top right hand corner of what exactly this looks like. We could see that there's their starting sequence number, and then the length is equivalent to our payload, so a length of 1432. This means if I were to add the starting sequence number plus the payload, this is the acknowledgement number that would be used to say that, yes, I got this specific frame. It's also why the next packet from the source starts with this very sequence number, because this one is picking up where the previous packet left off. The reason I include the timestamps as well is you could see this was at timestamp 14281. The acknowledgement didn't come until 14283, so 2 milliseconds of round trip time. But during that exact same period, if you look at your packet numbers, I went from 328,048 to 328,216. Nearly 160 packets were sent and received in that small 2 millisecond window. That's why my previous example had this datagram 4 and ACK for 1. Right when I was sending datagrams 4 and 5, I was getting the acknowledgement for number 1. The real world is going to see that same scenario, but on a much larger scale. Here we're only talking about 2 milliseconds, yet hundreds of packets were able to be sent and received during this time. And again, this is an extremely common mistake for engineers to make, and one that you should no longer do. And that is, if you see an acknowledgement number that is not acknowledging the packet with the same sequence number, it is the one immediately before it. Okay, so let's move on from this subject and focus on a few more things when it comes to measuring TCP performance. If we know the round trip time, aka the latency, the maximum segment size, and the window size, then it is possible to calculate the highest expected throughput for a given TCP flow. And in the coming slides, we're going to talk a little bit about how we can use some simple external calculators located on various websites in order to figure out what this looks like. Additionally, Wireshark also has some pretty interesting tools that allows us to deep dive into the protocol itself and figure out what, if anything, is changing. And these are the TCP window scaling graphs as well as the TCP throughput graphs. There's a lot of moving pieces within TCP, and this is also one of the reasons why we focused on getting two packet captures, one in the broken and one in the working. Because some of these things, like MSS, latency, maybe even window size, might be the same in both scenarios, but we need to try and find the deviations, which may explain why the throughput is lower than expected. Okay, so how do we actually make this sort of thing happen? Well, let's start with calculating the window size, because our window size are not going to be 1 packet or 10 packets. They're likely going to be significantly larger. And because it's constantly changing throughout the flow, TCP or Wireshark has a dedicated tool called the window scaling graph that makes this very easy to visualize. The way we accomplish this is by opening up any old packet capture that has TCP packets. In this example, I'm just picking a random packet within the flow. Really doesn't matter which one. And we could see here the gray bar indicates that this one is selected. Once I have a packet selected, up at the very top is the statistics option. This brings down a drop-down menu, and a little bit further down, I've omitted some of the output here. It'll say TCP stream graphs located near the bottom. If you mouse over that, you get another window, and you want to select the window scaling graph that you see here. This will make a new window appear that looks something like this. And there's quite a bit going on. Now, if for some reason you have a large TCP flow selected, I should probably also stipulate this works best for the larger packet flow. So you're going to need something with many thousands of packets. If you're not seeing any of these green bars or you don't see any activity, you may need to click the switch direction button down at the bottom, because TCP, given it can operate in both directions, both upload and download, it could be the packet you selected was in the opposite direction of what you're looking for. So once you have the appropriate direction selected, you also want to make sure you deselect the bytes output counter. This way we're looking only at receive window. And there's quite a bit going on. So let's talk about what are some of these different fields that we see. Every green line, or every green dot, is actually a packet and the window size at that point in time. We can see here the scale on the left tells us the window size here is 3 million bytes, or 3 megabytes. This will not work if you do not have the TCP three-way handshake, because the window scale, which allows you to go above 65,535, does not get captured. Now, when I'm looking at this capture, it's fairly easy to see, judging by the large block of green up at the top. Most of the time, we're around the 3 to 3.1 megabytes per second. But then something happens around this 40-second mark, and again around, let's just call this 45, where suddenly the window size drops down to 0. If a client tells the destination our new window size is 0, that effectively stops transmission. And so this would represent a pause or a delay in the data throughput, whereas here the client is able and willing to accept data up to a certain window size. Now, in addition to that graph, we have another one that could look at the actual throughput of the flow. And we follow a similar path. We select a packet, it could be the exact same one that you had before, and within the statistics menu, back to TCP stream graphs, this time we're going to select the throughput graph instead of the window scaling. When you select it, once again, a new window will pop up and it'll look something like this. Again, if you're not seeing any sort of lines, you may need to switch the direction. And I also want to make sure you deselect these segment lengths so that only throughput is selected in this view. Okay, let's talk about what it is that we're seeing here. Every single one of these gold dashes represents the throughput at that particular millisecond in time. And we're doing it by measuring literally every single packet in this one particular TCP socket. So we could tell that the vast majority of the time we're pretty high, maybe there's a little bit of a drop, we kind of recover, but going back to our window size was set to 0, we could see that there is a dramatic drop in our throughput. This is something the customer would have absolutely seen. Now, because it has this sharp line, this represents the packets that were still in transmission. So we were sending data, there was bytes in flight, then the window size got updated, but at that point, there was already data going towards the destination. There was no way to stop them, and that's why we see kind of this line that goes at an angle as opposed to just a straight down vertical drop like we did before. Now, the way I could tell what the actual throughput is on the column to the right here. Unfortunately, Wireshark makes it a little bit tricky by using the power multipliers, but essentially this says 2.5 times 10 to the 8 is this line here. We're going a little bit above that. Let's just call it 2.6 times 10 to the 8, which means we need to move our decimal place over by a factor of 8. So that'll be about 250 megabits per second. So to quickly summarize, based on what we just saw, I have a TCP flow where the customer was getting approximately 250 megabits per second on average, and TCP negotiated a window size of around 3.1 megabytes. The last piece of data I need to figure out how fast this flow could actually go is the round trip time. And this one is fairly simple. We just need to go to the three-way handshake and measure the amount of time between the first and second packet, or second and third, depending on if our capture was taken closer to the client or closer to the destination. Here we could see that the client initiated this SYN, and it took about 67 milliseconds for the SYN ACK to come back from the server. Okay, why does all this matter? I've got 250 megs per second plus a 3.1 meg window size and 67 milliseconds of round-trip latency. Well, remember from the beginning of this video, we talked about what's the maximum theoretical throughput for a flow if the window size is only 1 packet, or 10 packets with a 100 millisecond round trip time. Well, the same logic is going to apply here, but fortunately we have some calculators online that make it pretty easy. And this is one of the calculators that I prefer. I have the link right here. And when you open it, you're going to see a window similar to this. And all you need to do is plug in the values that you have. My bandwidth, in this case, the customer was connected using a 1 gig interface, so I put in 1000 megs. RTT is your round trip time measured in milliseconds. It was 67 per the previous slide. And then my window size in kilobytes is 3100 or 3.1 megabytes. When I calculate this, it tells me three pieces of information. The two that I really care about is one, what is the required TCP buffer to reach 1000 megs per second with a round trip time of 67? This means if I wanted to saturate my 1 gig link, knowing that we can send data at literally 1 gigabit per second, and knowing that the round trip time is 67 milliseconds, our window size would need to be about 8.1 megabytes in order for line rate transmission to be achieved on a 1 gig interface. But in this case, our window size is not 8.1, it's 3.1 megabytes per second, which means our maximum theoretical throughput with no packet loss whatsoever would be around 380 megabits per second. This is now how I can compare the customer's capture, look at it at the maximum theoretical throughput, and determine, is the customer reaching the maximum theoretical throughput, which may indicate that some of the settings within their TCP stream need to be modified, or does it indicate maybe something is happening on the network, such as packet loss, which is causing the performance to be lower than what the maximum theoretical throughput could be? So in our example, the expected throughput was around 380 megs, and we saw upper limits of 270, a difference of about 100 megabits per second. What are some of the things that can explain this? Well, first off is packet loss. If there's missing pieces of data, then that's going to slow down the transmission and the windows involved and may potentially bring those windows down to zero if there's enough loss. The other is what's known as a congestion window, and unfortunately, this is not viewable within the packet captures. And the way we can think about it is the window size that we've been talking about. That is simply the client telling the server, here's how much data you are allowed to send me. But the server has no obligation to send that much data. Servers, especially web servers or anything involving the internet, they do not want to waste bandwidth, especially if they have a lot of volume that they're dealing with. And so many of them will have what's known as a congestion window, where even though a client is asking for a faster speed, internally they will still rate limit or they may back off some of the flows if there's something like packet loss or something which might otherwise waste bandwidth. Again, there's no way to tell this from the packet captures. If anything, it's usually the lack of any data might indicate that we're dealing with a congestion window on one of the devices. And then finally, direct or indirect rate limiting in the form of something like a shaper or policer, which typically also causes packet loss, may be inducing some sort of delay and not immediately visible through the capture. So maybe it's adding a lot of extra latency, causing a lot of jitter, could be causing some retransmissions, but obviously this is something that would slow down the transfer even if these settings allow it to go higher. Now, when it comes to solving for these, let's first talk about packet loss. And as we discussed earlier, every single packet is going to have a sequence number that must be acknowledged by the endpoint. But if the packet goes missing, how do we know which individual piece was there? It's a combination of looking at the number of duplicate retransmissions or acknowledgments. And the way we can filter these out in Wireshark is with the tcp.analysis.retransmission filter or the tcp.analysis.duplicate_ACK. And there's a couple different flavors of these. We can see at the very top here I have some that are called TCP fast retransmission and some that are just called retransmission. Let's look at what a retransmission example looks like. Our client is going to start sending some sort of data packet. This will go to the server, and then the server will acknowledge it. That is the normal flow. But if for some reason the client goes to send a data packet and that packet is now lost on the network, lost on the network, the destination may not know that that packet was coming. So the client goes, I have not heard any acknowledgement from the server, but I should have. Your clients, when they start the three-way handshake, they do get a very general understanding of how long it should take to get an acknowledgement. So when the client sends this packet and it goes unacknowledged, the client says, I should have gotten an acknowledgement by now, so let me resend it just in case. And that's what we saw here for data packet 2. And this would be registered as a TCP retransmission. Because we didn't see an ACK, the client's internal counter expired and forced it to regenerate this packet on its own. Now, the alternative to this, where we actually use the acknowledgement numbers, is what's called the fast retransmission. So, same example. My client is going to start sending some data, but this time, some of the data is lost. The server can send a selective acknowledgement saying, I only got packets 1 and 3, 2 is missing. And here, because there's 3 packets, it'll send 3 acknowledgements. The client will then send the missing piece, as well as some of the other data it was planning on sending anyway, at which point, if they all make it, the server can acknowledge that, yes, I got not only the missing piece, but the additional pieces that you sent. Now, unfortunately, that is not an accurate depiction of reality. It's not going to be as simple as just sending a packet, getting an acknowledgement, or not getting acknowledgement. It happens a bit quicker and at a higher scale, similar to what we saw with the sequence and ACK numbers a bit earlier in this recording. When it comes to packet loss, there's actually quite a bit of delay and quite a bit of duplication that happens in order to kind of measure the latency and the amount of loss that's going on. So let's look at this diagram and see what I mean. Here our data packets are being sent across, but one of them goes missing. The destination now sees that some of the packets came in out of order, and that triggered it to start sending duplicate ACKs saying, I only got up to packet number 1 consecutively. Number 2 was missing. And as the client was sending data, some of those were still in flight, so all those additional packets that were not number 2 caused the server to send a duplicate ACK. Let's rewind and go through that a little bit more. There's a lot going on here, so let's step through it. So let's look at packet number 2, comes in, gets lost. Number 3 comes, that's when the server realizes something has gone missing. But all these packets were still being sent before we finally got this duplicate ACK, which would trigger us to send the missing packet. In this case, data packet number 2. Let's go back one more time and take a look at this from the ACK perspective. So loss, here's my ACK. Once I get the ACK, I retransmit number 2, and I continue acknowledging the way I was. And we could see, even though I lost a single packet, because of the rate at which I was transmitting and the delay between these sources and destinations, I ended up getting 3 duplicate acknowledgements telling the client, hey, the packet you just sent me was not number 2. If we were to expand this out into the real world, we could typically see tens or hundreds of duplicate acknowledgements, where, again, every time the server gets a packet that is not the one that is missing, it will send a dupe ACK. If there's a lot of latency, that will trigger many duplicate acts to be generated. And here, in a real world example, we could see that Wireshark is telling me this is the 252nd duplicate acknowledgement for packet number 494053. So we had near over 250 duplicate acts, and then down here is some more evidence of loss, but for a completely different packet. So the first one we see, we count as number 1. The second one we see is number 2, and 3, and 4. And this will go on likely until we get kind of a similar number around the 250 mark. So just because you have a large number of duplicate acts does not necessarily mean there was a lot of packet loss in one direction. Instead, it likely indicates that there's a good amount of latency between these two destinations, and if they were using a larger window size, it meant that there was a lot of bytes in flight. Okay, we're almost done with this section. The last thing that we need to cover is a bit about fragmentation, MSS adjust, and bears. Oh my. Okay, so how do we summarize fragmentation? Well, fragments are bad. Okay? Fragments are essentially a process-intensive way of further breaking up a packet that should have been broken up at the source. And when we need to do fragmentation, it often involves the CPU of a router or switch, which cannot even compare to the hardware forwarding capability of that same device. So if we're dealing with an instance of fragmentation in a TCP flow, typically this means something like pings might work and be loss-free, but our TCP transfers are slow and they generate high CPU on intermediate devices. Or if you're looking at a packet capture, you'll see a lot of different fragmented IP packets within the capture itself. Now, some of the causes of fragmentation are typically around the use of things like tunnels. If a customer is using something like a DMVPN tunnel, a GRE tunnel, even a CAPWAP tunnel, where a client's wireless traffic goes to an AP and then that AP tunnels it over to a wireless controller, if the clients don't know they're in a tunnel and they try to use the larger MTU, it will force intermediate devices to fragment that traffic. Well, how do we get around it? That's where MSS adjust comes in. Because the MSS value is negotiated only once at the three-way handshake, we can look for that and arbitrarily lower it. And I have here a quick demonstration. I also want to highlight one of the dangers about how fragmentation can also cause an excessive amount of packet loss. If we were to think about a super big packet, let's say we have this big 9,000 byte packet. If this was going over a 1,500 byte Ethernet network, I would need to break it up into 7 different pieces. So 1, 2, 3, 4, 5, 6, 7. Some of them are 1,500 bytes, some of them are 280 bytes in order to round out our 9,000. When this gets sent across the network, we're going to send them all individually. So the first packet goes, then the second, third, fourth, fifth, but let's pretend the sixth gets dropped. The receiver now has 6 out of the 7 pieces necessary to reassemble this big 9,000 byte frame. Because there's pieces missing, we need to retransmit the data. It will start sending duplicate acts for the entire 9,000 byte packet. There's no way to retransmit just a single 1,500 byte fragment, which means the entire 9,000 bytes needs to be sent, broken up, and then each individual piece needs to be resent across the network, even though they weren't necessarily lost. And it's only when all of the fragments make it to their destination that we will be able to consider it a success. So not only does this waste a lot of bandwidth, uses a lot of CPU resources, it's very slow, fragmentation overall is just a very bad thing. Now, as I said earlier, the way we fix it is through the adjust MSS or MSS adjust. It's been called both things. And that's where a router or switch that's in the path has the ability to recognize a three-way handshake and change it on the fly. Let's look at what this looks like from a host perspective. Here, host A is going to initiate a connection to server B. It's going to send a TCP SYN with an MSS of 1460. Essentially, host A is telling server B, you can send me a packet with a maximum individual payload size of 1460 bytes. The client now sends this across the network where it is intercepted by the client's default gateway. The gateway recognizes this and says, well, this is actually going across a tunnel. We need to change it. 1460 is too big, so I'm going to rewrite this TCP frame to a smaller value of 1360. It then takes that new TCP SYN, injects it in the same path, and sends it to the server. When the server gets it, it has no idea that this packet was just modified. It thinks that this is what the client asked for. The client said, you can send me a packet with a maximum individual payload size of 1360. This means that anything sent by the server will now be a maximum of 1360 bytes, or about 1400-ish when you include the IP headers, and 14, probably 16 or 18 with Ethernet headers. Assuming this happens bidirectionally for both the SYN and the SYN-ACK, this means that any SYNs generated by the host get rewritten to 1360, and any SYN-ACKs or SYNs generated by the server also get the same value. Now, all of the remaining TCP packets in this flow will use this smaller negotiated value. In terms of things that you need to look out for as a network engineer, keep in mind legacy Catalyst products, and I use legacy in terms of things like the Cat 4K or Cat 6K. When they had this IP TCP adjust MSS configured, they would change packets bidirectionally, meaning if gateway A was configured, it would do the packets from A to B, but would also adjust the packets from B to A. Cat 9K only performs this action on the ingress direction. That means if the adjust MSS feature was only configured on gateway A, traffic from A to B would be adjusted, but not from B to A. As a result, in one direction we might have fragmentation, and in the other it would be operating normally. There is an enhancement which at the time of this recording has not been resolved, so it's still open, where we make this bidirectional. But for now, treat this as a unidirectional feature where if you have fragmentation occurring on your network, make sure you apply it to both the source and destination devices so that the SYN and the SYN-ACK gets adjusted accordingly. And with that, this will conclude part 2 of the TCP deep dive. In part 3, we're going to apply everything we just learned to some common problem scenarios. I hope you stick around.